Welcome back to the Foundry, brought to you by Forge College. Now, if you caught our last explainer, you know we were really deep in the analytical weeds, dissecting analysis methods for Gulf Stream transactions. But today, well, we're shifting gears. I want you to think of your role today not just as a developer, but honestly as a master structural engineer. We're here to heavily reinforce our smart contract's structural integrity, just making absolutely sure that when the pressure is on in production, our code holds up flawlessly. So today's focus is improving coverage and documenting insights. Let's get into it.
Okay, let's dive into this master blueprint for our final safety checks. We'll be covering 1. Mind the coverage gap. 2. Mapping your missing tests. 3. Unit, fuzz, and invariants. 4. Writing optimization notes. 5. Proving the improvement. And 6. Ready for final assembly.
Section 1. Mind the coverage gap. Because we've all felt that universal developer frustration of thinking your codebase is perfectly secure, right up until you run a coverage report and see it glowing with untested red lines.
Section 2. Mapping your missing tests. It is time to turn those scary red lines into a concrete mapping of scenarios we actually need to test.
So, a coverage heat map. We've literally all been there, right? You write your code, your baseline test passed, and you're feeling like an absolute Web3 genius. But then you run Forge coverage and your screen just lights up with untested vulnerable lines. That anxiety-inducing wall of code is what we call a coverage heat map. Basically, it's a visual artifact that highlights the specific lines, conditional branches, and functions in your code that remain completely untested. Think of it exactly like an engineering thermal scan of a building. It's revealing the exact structural weak points where security risk is just silently leaking out.
And here is where the rubber really meets the road. We need some concrete, measurable targets for our critical modules. Take our token module, for instance. We need to bump that from a baseline of 62% up to a really solid 90%, and we'll do that by adding failure branches. Then we've got accounting, which needs to jump from 55% to 85%, and our Oracle module, we absolutely need to boost that from 70 up to a rock-solid 92% by deliberately mocking stale data feeds. You see, we aren't just guessing here, we have a very clear, numerical mission to hit for our capstone deliverable.
Section 3. Unit, fuzz, and invariants. Now that we've found the weaknesses, let's apply some reinforcements using targeted Foundry patterns.
And this brilliantly illustrates the difference in our approach. Consider a standard unit test, something like test_transfer_reverts for specific failure paths. It's great, but it's kind of like checking if your newly built roof holds up on a pleasant sunny day. On the flip side, we have the fuzz test. By using vm.assume to constrain randomized inputs, fuzzing is basically throwing unpredictable, chaotic weather patterns right at that exact same roof. You're not testing the sunny day anymore. You're literally testing for a hurricane.
To survive that hurricane, you're going to need a solid toolkit. Here are some quick Foundry troubleshooting hints for you. Need to bypass an only owner role check? Use vm.prank. Is some time-dependent logic keeping a branch stubbornly untested, while vm.warp is your literal time machine? And if your fuzz tests are failing just because of totally unrealistic random data, use vm.assume to constrain those fuzz inputs back to a valid domain.
Section 4. Writing optimization notes, because an engineer's job isn't actually done until the spec sheet is completely updated.
So we've written the tests, but writing an optimization note is a really meticulous process. Step 1, you state your hypothesis in one clear sentence. Step 2, provide the exact reproduction commands, right down to environment variables like forge_profile. Step 3, list out your specific test references and exact line numbers. And finally, step 4, lay out your suggested next steps. Why go into this level of detail? Well, because any other developer, or honestly your automated CI environment, absolutely must be able to reproduce the exact behavior you just verified.
Section 5. Proving the improvement. Let's visually prove that our new tests actually solve the problem.
Once you have those tests and your pristine optimization notes, it's time to generate fresh coverage reports using LCOV or HTML outputs. And so the crucial point is this. Local gaps often hide functional risk that the overall percentage masks. Coverage isn't just some vanity metric for your README file. I mean, an overall 90% coverage sounds amazing, but if that untested 10% happens to be your core accounting logic, yeah, your application is in serious trouble. We absolutely must commit to module-by-module verification.
Section 6. Ready for final assembly. Time to celebrate completing this project increment.
As we wrap up this explainer and position ourselves perfectly for the final assembly, I want to emphasize what we call the professional developer's triad. Traceability, which means linking every test directly back to an original coverage gap. Reproducibility, ensuring optimization notes allow anyone to get the very same results. And incremental verification, validating those improvements module by module. This triad is honestly the ultimate armor for any Web3 application, and it is totally the hallmark of a master builder. So I want to leave you with this final, somewhat provocative question. Your code works today, but will your tests prove it works tomorrow? That is the profound difference between simply hoping for the best and engineering for absolute certainty. Thank you so much for joining me on this explainer brought to you by Forge College. If you want to dive deeper into building unbreakable testing suites and explore a whole wealth of other amazing Web3 topics, head on over and visit forge.college. Keep building, keep testing, and I will see you in the final assembly.